Hello everyone, welcome to Design Education 2020. In this lecture, we will learn about the loads to be considered and the materials to be used in RCC design. So, let's get started with the technical definitions. First is characteristic value. Loads and materials are the primary parameters that affects the design of RCC structures. Both loads and materials are of varying nature, but for design it is required that we must arrive at some representative value. This representative value is known as characteristic value. Design value, the value to be used in designing that provides adequate or desired margin of safety is known as design value. Next is partial factor of safety. The ratio of the above two values greater than unity is known as partial factor of safety. Characteristic load. It is defined as that value of load which has 95% probability of not being exceeded during the life of structure. It can be determined using statistical and probabilistic principles, but this requires large statistical data. Since the data is not available widely, code recommends to take working loads decided in the past experience and judgments which are obtained from principle of equivalent load giving same maximum effect. Next is design load. It is given by FD. It is equals to gamma F times Fk, where Fk is characteristic load and gamma F is partial safety factor for load. Next is types of loads. The primary loads are dead load, live load and the other loads. Other load includes wind loads and earthquake loads. So let's move to dead loads. It includes the self weight of every member we are considering in the design, weight of the finishes like floor finishes, and the weight of partitions, walls and grills. Table shown on the next slide gives the unit weight of various materials used most commonly in the construction. These values are taken from IS 875-1987 Part 1. The values are tabulated in these two tables for various materials used in construction industry. Following table gives the simplified expressions to obtain dead load intensity of each building components. For beams and columns it's 25 BD, where B and D are in meters. Slabs it's 25 D, where D is the depth of slab which is in meters. Brick walls is 20 B, where B is the wall thickness in meters. And the last is RC grills and parapets. The expression for it is 25 T, where T is thickness of the RC grill or parapet wall in meters. We don't need to mug up these expressions. The numerical coefficient in these expressions is nothing but the unit weight of material we are using. Next is weight of finishes. The finish value is inclusive of weight of tile, mortar bed and underneath ceiling plaster. For rooms we can take it to be 0.75 to 1 kilonewton per meter square. For sanitary blocks it's 1.5 to 2.5 kilonewtons per meter square. For roof finishes including weight of waterproofing cores it's 1 to 2.5 kilonewtons per meter square. We have some additions and reductions in these values. So appropriate reduction in load can be considered for openings in external walls. No such reduction shall be considered for interior walls because normally there are no openings in these walls. Reduction for door opening is generally not made because it is balanced by increase in wall loads due to wall mountings, fixtures and cupboards. Separate loads shall be considered for lofts in rooms projecting outside the walls. Weight of members of common sizes are tabulated below. These are the most common depths for slab. Like for slab of 100 mm depth, the approximate weight is 2.5 kilonewtons per meter. For 150 mm it's 3.75 kilonewtons per meter. The weight of slab is calculated using the same expression of 25D. where D is depth of slab, which is to be taken in meters. Similarly, weight of beams and columns is calculated using the expression of 25 BD, where B is the width of column and D is the depth of column. So, for common sizes like 150 mm width and the depth is between 300 to 600 mm, the approximate intensity comes out to be 1 to 2.5 kilonewtons per meter. Next is live load. IS 875 1987 Part 2 deals with minimum imposed loads to be assumed on floors and roofs in the design of building. These are the minimum loads which should be taken into consideration for the purpose of structural safety. The table gives the minimum imposed load to be considered for residential buildings. Loads for other type of buildings can be taken from IS 875. From all the above considerations, for residential building spanning less than 3.5 meters for each individual entity such as rooms, stairs, balconies, etc., the total loads are roughly taken as what shown in the following table. Considering the slab thickness of 125 mm and choosing the floor finish and live load values from the relevant codes, we can get the total intensity as 6 kilonewtons per meter square. Similarly, we can get the values for cantilever balconies and stairs to be 8 kilonewton per meter square and 10 kilonewton per meter square respectively. The values obtained for balconies and stairs will be cross-checked when we will learn about the design of slabs and staircases. These values are the approximate values just for having the idea about what will be the load intensity roughly. Other than dead load and live load, the wind load and earthquake loads are the main loads required to be considered in building design, especially when the height of building exceeds 2 times the dimension transversed to the exposed wind face. Most of us have studied more or less about earthquake loads in our curriculum. Therefore, I am focusing more on wind loads. However, if you need me to discuss about basics of earthquake loads, you can drop a mail at mail ID given in the description box. I will make another video for same. Moving back to our discussion, wind loads are not critical in buildings of height up to 4 stories and which have infills in both directions in between columns and beams. Therefore, we do not consider the wind load effects when we are working on buildings up to 4 stories. But why? This is one of the interesting question. I will discuss this in the next slide, but before that, let us work on what are the critical load combinations. So let's move on critical load combinations. While designing a structure, all the load combinations in general are required to be considered and the structure is to be designed for the most critical of all. For high structures, due to pure transitory nature of wind, code allows 33% increase in permissible stresses in working stress design method when the effect of wind is considered. Whereas in LSM, the factor is reduced to 1.2 and the load combination becomes 1.2 times dead load plus live load plus wind load when the effect of wind load is considered. However, if the wind load is not considered, then the combination to be considered is 1.5 times dead load plus live load. Now, let us discuss the question why. For smaller height buildings, the dead load of concrete structures is so large as compared to wind loads that the actual increase in stress due to wind is less than the allowance due to safety factors given in design by code. Since for buildings up to 4 stories, wind load is neglected, the elements are to be designed only for critical combinations of dead load and live load. For critical load arrangements, we have two conditions of maximum and minimum loads. Code specifies different load factors. First is maximum load case. The combination for the same is 1.5 times dead load plus live load. The explanation for the factor 1.5 is that the load factor specified in Indian Standard Code is 1.5. The second load case is minimum load case. The expression for the combination is 0.9 times dead load. This is because minimum value of live load will be 0 and the load factor of 0.9, which is actually less than 1, is considered for stability of structure in the worst case scenario. Let's see the critical loading arrangements. These are maximum support moment, maximum span moment and the maximum support shear. Case 1 is maximum support moment and maximum support shear. Two adjacent spans under consideration shall be fully loaded with maximum design load, which is equal to 1.5 times dead load plus live load, whereas all other spans are loaded with minimum design loads, which is equals to 0.9 times dead load. Second arrangement is maximum span moment. The span under consideration and all other alternate spans shall be fully loaded with maximum design load of 1.5 times dead load plus live load, whereas all other spans will carry minimum design loads of 0.9 times dead load. Last case is the maximum negative moment in span. Span under consideration and all other alternate spans shall be loaded with minimum design load of 0.9 times dead load, whereas all other spans should carry maximum design load of 1.5 times dead load plus live load. That's all for part 1. In the next part, we will discuss about the materials and their properties. Specifically, we will discuss more about concrete and a little about reinforcements, as these are the two main ingredients of the RCC work. Thank you.